They call me Private Investigator 84. I crack cases and take names. Using math. It's a man's world, but who says a woman can't join in on the fun? I'm very good at my job.
By George, I cracked it. By George, I cracked it. By George, I cracked it.
One morning, I was up late working.
Listen, kid, here's your next case. It's a difficult one for a woman.
Oh, brother. Yes, another murder.
His case file informed me his name was Kenneth Harold Alexander Farley III. He owned a $1 trillion company in the ultra-competitive bee market. A slave to his work, he had little time to spend with his family, but kept them close to keep up public relations. His job seemed to take a toll on the family because on the night of April 28th, one of them decided to do him in.
Oh, hey, how are you doing? Wow, Tempur-Pedic mattresses sure are cheap right now. So, tell me, my son, wife, or mistress, how was your baseball game, library opening, or affair with another man? Wait, what are you doing with that knife? No, it can't be you!
I went to investigate the scene of the murder.
Wow, looks like somebody didn't play knife. Wow, I bet that cut deep. Looking sharp. Well played, criminal. Well played. Gonna keep that one. Alright, let's check out this murder. Air. 65 degrees. Just as I suspected. The temperature. I think I have all the evidence I need. But do you, they'll ask? Only time will tell.
First suspect was the son. He had an affinity for baseball and a reputation for partying too hard. I quickly ruled the son out of my suspects. He was at an away game all weekend, with numerous eyewitnesses to vouch where he was at all time. Our second suspect was his wife. She was a power-hungry businesswoman. They were married for 29 years, in love for none. It was a marriage of convenience.
Where were you on the night of April 28th? Well, I had to fire 3 workers. Budget cuts, you know. Anyways, they cried, so I had to deal with that. Next, that happened from 3 to 4. I was pretty efficient. After that, I came home, got dressed, and at approximately 5:15, I went to the opening of some dumb library for charity sort of thing. Have to keep my wrap up. I ended up staying there pretty late, just lounging around and getting pictures taken of me, probably until 1 a.m. You can check the security cameras.
Our final suspect was his mistress. She was a tissue salesman who wandered upon his door one day. She ended up staying for quite a long time.
Where were you on the night of April 28th? I was teaching a water aerobics class from 6 to 9, came home, took a shower, got my glam on, and then went on a wonderful date with the deceased brother at 10. We finished eating and everything around 11:30, so I came home, got my PJs on, and was asleep by 12. You were with her on Friday night? From 10 to 11:30? Alright, thank you. No, you're disgusting. Good night.
I was stumped. This was my hardest case yet. The son was no longer a suspect, so that left the wife and the mistress. They each had rock-hard alibis. Well, almost rock-hard alibis. No one could verify where the wife was from 4 to 5:15, and no one could verify where the mistress was from 9 to 10. But how could I find out when he was actually killed? turned to my trusted friend calculus to help me find an equation that would give me the temperature of the body at a specific time. To do this, I found a video on the line.
Hey guys, today I'm going to teach you all about Newton's law of cooling. Newton's law of cooling is a super incredible calculus function that basically says that the rate of change of temperature of an object is proportional to the difference between the temperature of the object minus the ambient temperature. Now, if we write out this equation, you're going to see that Newton's law of cooling looks like this. Change in temperature over change in time equals a negative constant that we'll call K times the temperature of the object minus the temperature of the surroundings. Now, if we want to find the temperature of an object at a time, we can get that equation from this, but we're going to have to do a little bit of calculus first. So let's go ahead and separate all the variables. So we're going to divide, so we're going to get the change in temperature divided by temperature minus temperature of the surroundings equals, multiply both sides by change in temperature and by change in time, and negative K dt. Then we integrate, and we're going to get ln of the absolute value of temperature minus temperature of the surroundings equals negative K times plus C, the constant of integration. Now, we're going to put everything to the power of E, and then that's going to cancel out the ln, and that will give us the absolute value of T minus temperature of the surroundings equals E to the negative K T plus C. Now, here we can go ahead and, since the exponents are added, we can separate that out into two separate E's multiplied together. Essentially, E to the C times E to the negative K T. Next, what we're going to do is, since E to the power of anything times E to the power of anything has to be a positive number, since E to the power of X can never be negative, we can go ahead and remove the absolute value. Then we're just going to add the temperature of the surroundings to both sides, which gives us T in terms of time equals E to the C times E to the negative K T plus temperature of the surroundings. Now, the only problem with this is that we have so many variables in here. Well, constants really, but we don't know what they are. So to go ahead and solve for what this constant right here is, we are going to go ahead and set time equal to 0. And so what you're going to get is the initial temperature of the object equals E to the C times E to the power of 0 plus temperature of the surroundings. Lastly, we're going to go ahead and turn E to the 0 to 1 and subtract the temperature of the surroundings from both sides, and you get initial temperature minus temperature of the surroundings equals E to the C. Then you can plug that back into this, and you're going to get the equation that temperature in terms of time equals temperature initial minus temperature of the surroundings times E to the negative KT plus temperature of the surroundings. And that's the equation that you're going to use.
I decided to use Newton's law of cooling to determine when the victim was murdered. For this particular case, the surrounding temperature, the time of the murder, was 65 degrees Fahrenheit. The victim's original temperature was 98.6 degrees Fahrenheit. At 4 o'clock, when the suspect was found, the temperature of his body was 70 degrees Fahrenheit, and an hour later, it was 68.73 degrees Fahrenheit. I then had all of the information I needed in order to plug different variables into the original equation. I set up two different equations, one centered at 4 o'clock, X amount of hours after the murder. The second one centered around 1 hour after the body was found, X plus 1. I used two different equations in order to isolate the constant K in order to determine when he was murdered. Once I finished writing the two equations, I realized I could simplify one. I could simplify e to the negative k times x plus 1 if I simply distributed out the negative k to the x and the 1. Therefore, I would get e to the negative kx times e to the negative k. Since I now had both my equations completely simplified, I could now start solving the first one. First off, I subtracted 65 from 70. Then I subtracted 65 from 98.6 and got 33.6. Then I divided 5 by 33.6, so my equation was 5 over 33.6 equals e to the negative kx. Then I did the exact same thing on my second equation. I subtracted 65 from 68.73 and got 3.73. Then, of course, 33.6, like in the last equation, times e to the negative k times e to the negative x. I then divided 3.73 by 33.6 and got e to the negative kx times e to the negative k. I realized that I had already solved that in my previous equation and could just plug e to the negative kx into my current equation. To get the variables on one side of the equation, I multiplied both sides by the reciprocal of 5 over 33.6. I ended up getting 3.73 over 5 equals e to the negative k. In order to get rid of the e, I took the natural log of both sides. That ended up getting me that natural log of 3.73 over 5 equals negative k. The natural log of 3.73 over 5 into my handy-dandy calculator and got 0.293 equals negative k. I multiplied both sides by negative 1 and got k equals 0.293. Now that I finally had the last missing puzzle piece in my equation, I was able to just solve for x. I plugged negative k back into my original equation, centered around 4 a.m., the time when the body was found. When the body was first found, it was 70 degrees Fahrenheit, so I was just able to plug 70 degrees in as I had before, and subtracted 65 from both sides. Then I divided 5 by 33.6, equal to e to the negative 0.293x. Then I took the natural log of both sides to get rid of the e and got the natural log of 5 over 33.6 was equal to negative 0.293x. I plugged the natural log of 5 over 33.6 into my calculator and got negative 1.9051, which is of course equal to negative 0.293x. So divided by negative 2.93 would equal 6.5 equals x. The 6.5 that we solved for represents the hours since the murder. It was time to put it all together. The body was found at 4 a.m. The hours since the murder was 6.5 hours. 6.5 hours before 4 a.m. would be 9:30 p.m. the night before. There was only one suspect whose alibi didn't match up during the times from 9 to 10.
The only logical explanation is that it was you. No, Tish, you. No, you killed him. You're right. I killed him. And I'd do it again. When he dies, I get $1 trillion. Do you know how many nail polishes you can buy with $1 trillion?
You're not going to be buying many nail polishes in jail.
No.
I had cracked the case once and for all.
Victory for working women everywhere!